Okay, so we're going to go ahead and now talk about thiols to finish up chapter 12, and then we'll begin chapter 13. Your first test is just going to be over chapters 10, 11, and 12. Okay, so even though we're going to start the other chapters, those won't be on the first test. Okay, just these first 3 chapters. That's what you're going to have on your first test. Okay? Okay. So thiols are sulfur-containing functional groups that you can add to these molecules. And they have the general formula R being the carbon chain, and then an SH. Okay? So they're very similar to alcohols. That's why they stuck it into this chapter, because if you replace the O with an S, then you get an SH instead of an OH. But it would be very similar in its structure. So like this, H, SH. 2 lone pairs right here are OH. Okay, and that is because O and S are in the same column of the periodic table. So they have very similar chemical reactivities. Now, physical property-wise, the OH would still have higher melting and boiling temperatures than an SH, because OH would hydrogen bond, whereas SH would not. Okay, so that would be one of the main differences between them. Okay, so this is a thiol group. When you're looking at the names of thiols, we're going to follow our basic rules. Okay, this is a dithiol. It's on an ethane molecule, and you have it on positions 1 and 2. So it's 1, 2, ethane dithiol. So we'd name that one. Here's just one of the ethane, on ethane also. So it's on carbon 1. It has to be either way. Doesn't matter which one it's on. Okay, so that's just going to be ethane thiol. Here you have a methyl and you have a thiol. Okay, and it's going to be 1, 2, 3 methyl. And the thiol group is going to take the precedence. That's why we numbered it that way. Instead of it being on carbon 4, we put it on carbon 1. And carbon 3 is going to have the methyl group on it. So it's 3 methyl, 1 butane thiol. Okay? So with alcohols, you would drop the N in and you call it ol, right? So here you're not really doing that. You're just tacking on thiol onto the name. Butane thiol. Ethane dithiol. Pentane dithiol. So here we have another dithiol, right? So carbon 1, 2, 3, 4, 5. Carbons 1 and 4 have the thiols. 1, 4 pentane dithiol. So you're going to put the whole name and then put a thiol onto the end of it. Okay, so that would be how you identify the names for these thiols. So thiols are not very pleasant molecules. Okay, so if you take an alcohol, alcohols have more of these kind of sweet aromas to them. They're much more pleasant. But then if you were to replace that with an SH, and the OH with an SH, it would stink. Okay? So these sulfur-containing groups are very stinky. We don't like them. Okay? They're very noxious to us. So here you can see as the scent of a skunk, okay, has these thiol groups on it that give it its noxious aroma that is not very pleasant. Okay, versus these plants down here, these flowers, which have the OH groups attached, which make it much more of a pleasant smell. Okay. All right. This one particularly also has one of these aromatic groups, which would be much more pleasant as well. Okay. So, and that's kind of the idea there. SHs, stinky. OHs, not stinky. Okay. So, much more pleasant. All right. Now, our proteins, this SH group, this thiol group, is actually a really important aspect of our proteins. So there is a amino acid, which is one of the building blocks of proteins, that contains a thiol, and that is cysteine. Cysteine has an SH group attached to it. Okay, so here's the SH of cysteine. So this is the amino acid cysteine. Okay, this whole thing right here is the amino acid cysteine. This is also a cysteine amino acid. And what happens is when one cysteine comes in contact with another cysteine, they react. They react together, and they actually form what we call a sulfur bridge, or a disulfide bridge. And that linkage is really important in the structure of proteins because it kind of links pieces of folded protein in place. It holds them in place so that when they don't fall apart so easily, and they'll retain their structure better that way. So here's an example of, let's say, a protein chain, which is a peptide chain. And so each of those circles represents a different amino acid. And so you're building this peptide. And as you do so, you strategically put cysteines in specific positions and as they come in contact with one another, as it folds up, so this protein starts to fold, and it will stabilize itself by the cysteines interacting and forming these disulfide bridges. And that locks those pieces in place. Because normally you could unfold it with just a relatively small amount of energy. But as you lock it with those cysteines, that holds it in place even better. It's going to require much more energy to denature that protein, to break it open, to unfold it. Okay? So these cysteine bridges become very important secondary structures of our proteins. Okay? Because they're going to hold the folds in place where they belong. Okay. Okay, so that's kind of the end of chapter 12. We're going to review how to make alcohols, the preparation of alcohols, the dehydration, oxidation of these, and the dehydration synthesis of ethers as well. Okay, so we're going to look at the different reactions of those. Okay, so if I have, let's just make that bigger. If I have an alkene and I do an addition reaction with water, I'm going to hydrate it. If I do a hydration with this water, water is going to break up into two pieces. One of the hydrogens is going to go onto one of the carbons, and the OH is going to go on to the other one. That is going to produce an alcohol, an OH, right? Okay? All right. Now, what rule do we follow for that? This is a very simple, there's no rule followed here, but let's say that this was a longer chain of carbons. What rule would we follow? That's right. The hydrogen would go to the one with more hydrogens. So if this instead was wow. Okay, strange. Okay, it doesn't want me to write there. Don't let me write it all. Let's try this again. Okay, there's all my scribbling right there. Okay, so if this was a longer chain, like C, H, H, double bond, C, H, C, H, H. Okay, so now in this case, when that double bond breaks, it's going to become a single bond, and I'm going to be able to add one thing to each of those carbons. What's going to get added to this carbon? Hydrogen. The majority of the time, that hydrogen will go there, and on the other carbon, you'll get the OH. Okay? That's the rule. Hydrogen to the carbon with the most hydrogens, right? Now, does that mean the other product doesn't exist? That's the minor product. It does exist. You do get that. It just might be 60-40, okay? Or 70-30. So it does exist. It just exists to a lesser extent, okay? But usually if they're asking for the product and they don't specify which one, then give the major product. That's the major one. But usually they should say, what is the major product of this reaction? All right? Okay, so hydrogen there. OH goes there. Okay. So let's take a look at these three situations. A primary alcohol. What identifies this as a primary alcohol? Why can I call it that? So this carbon is connected to how many other carbons? One in the R group, right? Okay. That makes it primary. That makes it a primary carbon, which is true. It's a terminal carbon with the OH. The OH is attached to that terminal carbon there. Okay? So that's a primary alcohol. Primary alcohols will oxidize into aldehydes. The formula, general formula of an aldehyde is R group attached to a terminal carbon with a double bonded oxygen and a hydrogen. Okay, so that's the functional group of an aldehyde. Okay. This terminal carbon is where the oxygen is present. And I basically took it, I broke, or not broke, but I took off these hydrogens. Okay. And I formed a new bond here. This one went away. And I formed that double bond onto that oxygen. And you would produce water as well from that reaction. Okay, oxidation of a secondary alcohol. Once again, you're going to break the bond on that hydrogen. You're going to break the bond on this hydrogen and oxygen. And you're going to form a double bond there. Okay. And you'll produce a ketone. How do you know the difference between a ketone and an aldehyde? That's right. How many carbons? 2. Okay. It's connected to 2 carbons. All right. That's because this was a what type of alcohol? Secondary. Secondary alcohols are attached to 2 carbons. And they produce ketones. So primary alcohol will produce a aldehyde. secondary alcohols will produce a ketone. And tertiary alcohols will produce nothing, right? They cannot be oxidized, so you can't form anything there. Because essentially, those R groups are all carbons. You don't have any more hydrogens to take off to make that double bond with. Okay? So to form that double bond, you want to be able to remove a hydrogen from the carbon and then form the double bond. But in a tertiary alcohol, you don't have that capability to do that. Okay? All right. Now, what if you started out with an aldehyde or a ketone? Okay? And you reduced it with hydrogen. You would form an alcohol. If it was an aldehyde, what alcohol would you form? Primary, good. And if it was a ketone, you would form a secondary alcohol. All right, so it's just the opposite. So in one direction, you're oxidizing it. Now that O doesn't stand for oxygen. It stands for an oxidizing agent. Oxidizing agents can be things like KMnO2, HClO3. Okay, they can be things like that. Potassium permanganate, sodium hypochlorite. Okay, those are oxidizing agents. So you just need an oxidizing agent, not oxygen, oxidizing agent that will allow for the oxidation of those alcohols. And then here, you're causing the reduction using hydrogen. So you're going backwards. Okay? And you're going to form those primary or secondary alcohols depending on what you're starting with. Okay, dehydration of alcohols is where, so the preparation of an alcohol would be where you have an alkene, you're breaking the double bond, you're forming the alcohol with water. So if you're doing the reverse of that, you're starting out with an alcohol and you're dehydrating it. That means you're going to pull out water, whereas before you're putting water into. Now I'm pulling water out of. Okay? So the result of that is an alkene and water. Okay, if I was going to dehydrate it. So the synthesis of an ether. Ether is where the oxygen is embedded into the carbon chain. Instead of being on the outside of the carbon chain, it's part of the chain. Okay, and with that, I would have two different alcohols, alcohol R1, alcohol R2, and as those two alcohols react, okay, you stick the R group on either side of the oxygen, and then you have water produced as well, coming off. Okay? So a lot of this is about accounting for everything that you have. Like, here I have an oxygen, here I have an oxygen. When I form the ether, I'm only going to have one oxygen, but I'll be able to put both R groups onto that one oxygen. And then what's going to be left? Water. Okay? With H2O. That's what's going to be left. Oops. Put that back. All right. So those are the reactions from this chapter. Okay, make sure you're familiar with those and how you would write the synthesis of these different items. Okay, and then let's start into chapter 13 here. Okay, now we're going to talk about aldehydes and ketones, which is a good thing to transition us from alcohols into aldehydes and ketones, because we can produce those from alcohols, right? So their physical characteristics are going to be different than alcohols because alcohols hydrogen bond. So why doesn't, here's an aldehyde, why doesn't this aldehyde, wow. Let's try this. Didn't help. Okay, chapter 13, there we go. Okay, why doesn't this aldehyde hydrogen bond? What would it need to hydrogen bond? Yeah, it would need a hydrogen bonded directly to the oxygen. Oxygen itself does not hydrogen bond. The oxygen has to have a hydrogen bound directly to it in order for that oxygen to be able to hydrogen bond with the hydrogen of another OH group. Okay, so just oxygen itself does not create that kind of situation. Now, that oxygen is going to have a polarity to it. It's going to be polar, but it's not going to hydrogen bond. So polar molecules will have high melting and boiling temperatures compared to nonpolar ones, but hydrogen bonding is going to have a greater effect than even a polar molecule. Okay, so this is polar, but it doesn't hydrogen bond, which is going to make it have different characteristics than alcohols that do hydrogen bond with the OH group that's attached to them. Okay, so here we still have a polar molecule. That oxygen is polar. It's going to be partially negative, and it's going to cause this molecule to become partially positive down here. Okay, but it is not going to hydrogen bond. All right. So you can see you're still going to get these polar interactions where you have the partially negative oxygen and partially positive carbon here. Okay, and those are going to form dipole attractions, but not hydrogen bonding attractions. Okay. Okay. So they cannot form intermolecular hydrogen bonds, but water can form a hydrogen bond to them. So if I had a water molecule that does hydrogen bond, then the hydrogen of the water could hydrogen bond to the carbonyl oxygen there. Okay? So that oxygen of the carbonyl group could hydrogen bond to a water, which does hydrogen bond, but to themselves, they don't hydrogen bond. There's no hydrogen bonding there. Okay? Even though over here on these R groups you have carbons bonded to hydrogens, there won't be hydrogen bonding occurring there. Okay? It needs to be directly on the oxygen. Okay, so carbonyls boil at higher temperatures than hydrocarbons, which are nonpolar, and then ethers. Okay, ethers are also polar, but they're kind of embedded in that carbon chain, and so they kind of get forgotten about as far as their polarity goes. They're not going to be as polar as these carbonyl aldehydes and ketones. Okay, but they're going to boil at lower temperatures than alcohols because alcohols hydrogen bond. Okay, so as far as the chemical or physical differences between these aldehydes and ketones compared to the alcohols, that's the main difference. The reason the alcohols have higher melting and boiling temperatures is because they will hydrogen bond, and these aldehydes and ketones will not. Okay, so here is an alkane. Here is an ether. Here is an alcohol. Here is an aldehyde, and here is a ketone. They all have almost the exact same molecular weight. So they all weigh almost the same, which means the differences in their physical properties are not due to their mass. Because the mass is pretty much the same, about 60. Okay? But the boiling temperatures are very, very different between things like the alkane versus all of these, which are polar. And the way I can recognize they're polar is simply because they have an oxygen. Usually when you put an oxygen on something, that's going to cause that thing to become polar. Because oxygen is going to have 2 lone pairs on its structure. It's just the way it is. It's going to make 2 bonds and have 2 lone pairs, which bends whatever molecule it's on and makes it polar. Okay? So that oxygen-containing molecule is going to be polar. But then the further question is, does it hydrogen bond? No. 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 Yes. Of those 4, the only one that hydrogen bonds is the alcohol. The others do not. Okay? So here is, even this aldehyde, you almost mistakenly think, oh, well, that's right there on the oxygen. It's not, it's on the carbon, right? So that hydrogen does not cause hydrogen bonding there. This oxygen will not hydrogen bond, okay, with another one of these molecules. So they do not. And you can see that in their boiling point, 49 degrees Celsius, 56. Now, between the aldehyde and the ketone, there's not a whole lot of difference between those boiling temperatures. There's not a lot. Okay? So that's not where the biggest difference is going to come. It simply is going to come from the fact that it doesn't hydrogen bond, and alcohols do. Okay, aldehydes. So now, alcohols end with what? O-L. O. O, right? They're alcohols. They're alcohols. So they're O's. Aldehydes, however, are going to end with all. There's not a lot of difference in how those sound. So, yeah. But make sure that you're writing it with the OL or the AL depending on what it is. Okay? So here, this is an aldehyde. It's the simplest aldehyde. Okay? It has a single carbon, double bonded to an oxygen, and single bonded to 2 hydrogens. So, 1 carbon, methanol, okay, or I should say methane. Methane, change the ending, and you're going to get the AL, methanol. Okay, methanol. That's formaldehyde. It's also formaldehyde. That's its common name. Okay, so along with its IUPAC name, go ahead and learn that common name for the simplest aldehyde, formaldehyde. I think formaldehyde's pretty you guys have heard that term, so hopefully that won't be too hard to remember. Formaldehyde, right, for methanol. Here's ethanol, 2 carbon aldehyde. And with these aldehydes, it's always on the end. Carbon, double bonded oxygen, the carbonyl is always at the end of the chain. So you don't have to say where it is, because you call it an al, you know where it is. It's at carbon 1. It's always at carbon 1 then. So this is ethanal, acetaldehyde. Okay? Acetaldehyde is for 2 carbons. So we have formaldehyde, acetaldehyde, methanol, ethanol. Okay? 3 carbons. Propanol, propanaldehyde. Okay? That one's not as common. I would focus mostly on those first 2, formaldehyde and acetaldehyde. You'll probably see those ones again. Okay? All right. So naming them, you're going to find the parent chain, count the carbons in it, drop the ending, and put an al. Okay. Number it from the carbonyl in. Number the substituents. Okay. So here is carbon 1. I don't have to say that the al is on carbon 1, so I don't. It's unnecessary. But I do need to specify where this methyl group is, so I say 2-methyl pentanal. Okay? So that's a pretty straightforward way to see that. Okay. Now, this is a way that you will need to identify or the numbering system on these aldehydes, okay? And that is through alpha, beta, gamma, delta. Okay? So, the way this works is, so if I have a 5-carbon chain here, 1, 2, 3, 4, 5, okay? You would probably want to say that if you're saying alpha, beta, gamma, you're going to start with alpha on carbon 1. But that's not true. Because the alpha, beta, gamma system is coming from what is the first carbon after the carbonyl. What is the alpha carbon to the carbonyl? So here, carbon 2 is always the alpha carbon. And then you start from there. Alpha, beta, gamma, delta. Okay? So here, if I was going to name it by IUPAC, I would say 2-methyl pentanal. Okay? But if it was a 5-carbon aldehyde, then actually for 5, with the common name, you'll change it from penta to viralda. Okay? And now viralda is going to stand for 5 with the alpha, beta, gamma labeling. Okay? So if I'm going to use alpha, beta, gamma, whenever it's 5, I'm going to use viralda. Okay? So alpha methyl viraldehyde. Here, now the methyl group is on the beta carbon or carbon 3. Okay, so 3-methyl pentanal will be beta methyl viraldehyde. Okay, so those 5 carbons, that's one of the only ones that really the name changes from penta to viralda. Okay, was for the 5-carbon one. But the other ones, it pretty much stays the same. Okay. Okay, so methanol was forma, ethanol was aceta, propanol, propanaldehyde, I'll change there, butanol, butyraldehyde, so this one becomes butyra, okay, and then pentanol will be viralda. Those will all be the aldehydes. And this kind of naming system goes for common names for a lot of things. Okay? Now not only for the common names of aldehydes, but you'll see these terms also used in other things, like when we're talking about acids, formic acid, acetic acid, propionic acid, butyric acid. Okay, so you're going to see those names again, and you'll be able to recognize what that means. 1, 2, 3, 4, or 5. Okay. Okay. So that's for those 5. Those will be the common names, and then you would use the alpha, beta, gamma system with them. Okay. So if it was butyraldehyde, and you had something off right here, let's just say it's a methyl. That's alpha, beta, beta methyl butyraldehyde. Okay, that's how that would work. This carbon right here doesn't count in the alpha beta labeling. Okay, so alpha beta comes after the carbonyl. All right, now let's look at ketones. So your simplest ketone has to have at least 3 carbons. Okay? Because it won't be a ketone if you don't have at least 3 carbons. If you have only 2 carbons, then you're an aldehyde. If you have only 1 carbon, you're an aldehyde. So 1 carbon or 2 carbons, you have to be an aldehyde. If you go to 3 carbons, you could be an aldehyde or a ketone. Okay? So the simplest ketone is propanone. And what you'll notice is that when you're naming these, now we're ending the name with one, O-N-E. Okay? So we're with aldehydes, it's al. With ketones, it's one, O-N-E. Okay? So indicate the position of the carbonyl carbon, and that is because that's unlike, I should say, aldehydes, because with aldehydes you didn't have to do that because it was always carbon 1. But with ketones, it can't be carbon 1, but it could be carbon 2, or it could be carbon 3, etc. Okay? Now with this first example, propanone, I did not have to specify 2 propanone. There is only one possibility if it's propanone. It's right in the middle. That's it. Okay? All right. So I didn't have to do it for that. No number necessary there. But when I move to 4 carbons, now, well, actually, okay. So it's still same thing. Now I don't. Sorry. 5 or more, you do. Okay? But for 4 carbons, because it's just either, it has to be the second carbon. With either way you put it on whichever carbon, it's always going to be the second carbon. Okay? So butanone. But once you move to 5, now you need to specify whether it's 2 or 3. Because it could be either 1, 2, or 3. Okay? But for propanone and butanone, you don't. Now there are common names for those two. Acetone will be the common name for this simple ketone. That's the main one you need to learn. Okay? This one, the next one, the common name is you would be able to derive because it's a methyl here and it's an ethyl here on either side of the carbonyl carbon. And so it's methyl ethyl ketone. Okay? That mimics very well how you named ethers. Okay? Methyl ethyl ketone. When you go back and look at how to name those ethers, okay, it's very much like that. Okay? So here we have a methyl here. 1, 2, 3, 4, 5 carbons there. So this oxy group is attached to the pentane methoxy, right? So it's like the two sides. You have to appreciate both sides of that. Okay? Same thing here. Okay? It's the methyl and then it's an ethyl ketone. Okay? So you have to appreciate both of those sides. But, okay, so this, the main difference is that 1, 2, 3, 4, 5 versus 1, 2, 3 is that the ketone is going to go to the should be 5, the side with the most carbons. Okay, so this will be the propyl ketone. I should number it like this.
It's not right.
Sorry?
It's not right.
What's that? Happened.